So today I am going to present the work that I have developed during the completion of my PhD thesis entitled Numerical Modeling of Impulsive Loads using the Smoothed Particle Hydrodynamics method. This thesis has been developed in the context of the program in mathematical engineering, statistics, and operational research. My PhD supervisors have been Professor Fabricio Macialan and Antonio Souto Iglesias. So the contents of my presentation are the following. I will first make a brief introduction in which I will present the industrial motivation for this work, as well as give some details regarding SPH that are worth having in mind from the beginning. Second, I will present in a more extensive way the SPH method, focusing on those aspects that are relevant in order to understand the rest of my presentation. After that, I will talk about what I believe is the most relevant part of this thesis, and it's also the most extensive, covering the convergence of SPH. Other related mathematical topics such as consistency, stability, the treatment of boundary conditions, or energy balance will also be addressed. After that, I will present an application case. This chapter is divided into two parts. First, I will present some experiments that have been carried out at the model busing in this faculty. And second, I will present some numerical experiments that have been performed in order to reproduce these experimental results. This presentation will be closed by collecting some conclusions and ideas for future work. So, effectively computing impulsive loads is a challenging task in the context of the offshore industry. In particular, recently attention has been paid to the development of stable, cheap, and easy to install floating platforms for wind energy turbines. In the design process of these platforms, it is a crucial step, the determination of the maximum design pressure, so that the scaling of the structure could be optimized. These maximum pressures are usually linked to violent phenomena, such as breaking waves, where impulsive loads are involved. An impulsive load is a quick and rapid increment in the pressure field that leads to a type of force that we call impulsive load. So, as in any other engineering problem, numerical simulations are an interesting tool. They are cheaper than experiments, but on the other hand, the industry needs the results to be reliable. So among the different computational fluid dynamics methods, for instance, finite volume method, finite element method, SPH is interesting because it presents certain features that make it preferable in order to simulate this type of phenomena that we shall discuss later. There are some works addressing the calculation of impulsive loads in the context of SPH, but the wide application at the industrial level of SPH is prevented due in part to the lack of a solid mathematical foundation regarding the convergence of the method. There are, nonetheless, interesting works addressing the convergence. I have in mind, for instance, the works by Ben Musa and Villa, as well as the work by Franz and Wendland, published in 2018, where the discrete SPH version applied to the Euler equations was addressed. They show that this SPH algorithm converges, but they do not take into account diffusive terms. So, with this in mind, the broad goal of this thesis is to deepen into the mathematical grounds of the Smoothed Particle Hydrodynamics method and enhance its applicability to relevant fluid dynamics problems, paying special attention to the computation of impulsive loads. Now, among the different features that make SPH interesting, we find its Lagrangian nature. So, what does it mean to be a Lagrangian particle-based method? Basically, and having in mind the difference between Eulerian and Lagrangian methods, an Eulerian method consists on considering the fluid properties as continuous fields, and then chose a discrete fixed grid where we discretize these fields, and with these discrete fields, we build the algorithm. On the other hand, in the Lagrangian framework, particles are considered discrete from the beginning that carry the properties of the fluid and which move according to a discrete version of our motion equations, in this case, the Navier-Stokes equation. Now, regarding SPH, it can also be seen as a two-step approximation method. In a first step, we substitute our functions by this convolution type operator involving a special function called kernel. Note that I say convolution type instead of just convolution, because here the domain of integration is the fluid domain, which in general won't be the same as the whole space. Therefore, this integral is not in general a convolution. We will also later discuss about this. Now, the kernel, it's a type of a sort of Gaussian function, like this one depicted here, which is asked to satisfy certain properties that we also discuss later. This level of approximation is governed by the smoothing length. The smoothing length is a certain measure of the kernel's compact support, as the kernel in general is asked to be compactly supported. Now, at a second level of approximation, this integral is approximated by a simple quadrature, where the evaluation points that are denoted here by xg coincide with the particle positions, and here the Langrangian nature of the method. This level of approximation is governed by the interparticle distance. Now, SPHERIC is the international community of researchers and industrials interested in SPH. Within this framework, what we know by SPHERIC SPH grand challenges are defined. These grand challenges are convergence, consistency, and stability, boundary conditions, adaptivity, coupling to other models, and applicability to industry. In this thesis, mainly the first of these topics, but also boundary conditions and applicability to industry will be covered. With this in mind, the objectives of this thesis can be summarized as follows. First, gain insight into the convergence, consistency, and stability grand challenge. Second, present new validation cases involving complex geometries, so that these experiments allowing to validate SPH against cases that already represent the complexity of real-life applications. Enhance the applicability of SPH to industrial cases by presenting validations. And finally, improve the capabilities of the open source software Aqua GPU-SPH. Aqua is an SPH solver first presented by José Luis Cercospita in 2015, which has been mainly developed within this faculty. Now, the goals attained concerning these objectives are the following. So for the first one, the convergence of diffusive SPH equations as well as the hydrostatic equation has been established. Second, the influence of the time integration scheme in the energy conservation has also been addressed. And concerning this also, an implicit time integrator scheme has been used, showing some interesting, driving to some interesting conclusions. Finally, the influence of the choice of the kernel in the convergence and other properties of the method has also been assessed. Concerning the second objective, a dam break case has been presented in this thesis, where an obstacle is included inducing three-dimensional effects of the flow. These results have been statistically characterized. Concerning the applicability, simulations using Aqua GPU-SPH have been carried out, reproducing these experimental results. And regarding the capabilities of Aqua, new features have been implemented in order to perform the simulations aforementioned, mainly concerning the implementation of boundary conditions when different kernels are involved. So now I will briefly present the fundamentals of the SPH method. So as we are concerned about fluid dynamics, I will start by presenting the Navier-Stokes equations that I consider. These are not the most relevant version of these equations. On the other hand, this represents the representation of a weakly compressible Newtonian fluid. As always, we have the continuity equation, the momentum equation, an equation of state relating pressure and density, and as we are within a Langrangian formalism, a way to compute the trajectories by stating that the velocity is the material derivative of the position. Now, in order to place these results in the whole picture of SPH, I would like to mention two possible approaches for SPH. So on the one hand, we can consider it from the beginning as a system of n particles, where discrete variables are defined, from which we reconstruct the smooth fields that are the SPH fields, and which should satisfy the Navier-Stokes equation. On the other hand, we can consider the method by an approximation of the Navier-Stokes equation. So we start by considering the exact equations, and then by these two-stage approximation method that I have described, we arrive at the SPH fields. Now, the focus on this thesis will be set in the study of the SPH formalism at the integral level. I will be showing several numerical experiments that we have carried out in order to verify the theoretical results. So in order that these solutions that are obtained in this experiment to actually approximate the SPH solution at the integral level, we need the interparticle distance over smoothing length ratio, that I will in general call eta in the following, to be small. This is achieved in most of the simulations that I will present by considering that the interparticle distance tends to zero much faster than the smoothing length. However, I will also present some cases and also some analytical studies about the case where this ratio is kept constant. This is interesting because it is a common practice between SPH users. But in general, as I already said, the focus will be set at the integral level. So regarding the kernel, it is a very relevant function in the context of SPH. So it is defined through scaling using the smoothing length, a radial function. The radial nature of the kernel plays a relevant role. We will discuss about this when talking about the convergence. And apart from being radial, the kernel is asked to satisfy other conditions, for instance, being integrable, differentiable, of compact support, and that its integral is equal to 1. Recently, there is another property that has been considered interesting by SPH practitioners. That is the fact that the kernel has a positive Fourier transform. So in 1995, Holger Wendland presented his already famous Wendland kernels, which are piecewise polynomial, positive, definite, and compactly supported radial functions of minimal degree. Actually, Wendland showed in his article that these functions are unique. So for a given dimension and smoothness, these functions are the unique that are of minimal degree. Later, Denen and Ali in 2012 showed that using functions with positive Fourier transform, by the way, the Wendland kernels do have positive Fourier transform, helps in avoiding the pairing stability phenomenon. So they understand that these functions were preferable among other kernels. Later on, we will be discussing whether this property is so important in the context of the convergence at the integral level. Now, here I have shown a couple of examples of kernels. So in the left, we have the radial profile of the kernels, namely the 3 Wendland kernels and also the cubic and linear spline. And on the right, you see the radial profile of the kernel's derivative. I would like to mention here the fact that recent research, like the works by Damien Biolot and collaborators, showed the interest in using the standard deviation as a scaling parameter instead of the smoothing length. I must admit that I agree to a certain extent with these considerations, but on the other hand, there are some interesting points in using the smoothing length. I won't discuss about that, just thought it was worth mentioning. Okay, so this is the discrete version of the Navier-Stokes equations that I will be considering. So first, we have the continuity equation where there is the discrete version of the divergence operator appearing. Now the momentum equation with the discrete version of the gradient of the pressure, and some version of the Laplacian. Here in particular, I have considered the Morris Laplacian, but there is also the Monahan Laplacian, which we will later discuss. Also, we have the equation of state and the Langrangian formalism. So you may have noticed that there are 2 extra terms that are introduced at the discrete level. The presence of these terms is relevant in order to attain that the good properties are conserved, in particular here, energy and momentum. These terms also vanish at the continuous level, so are consistent with the integral definition of SPH, as we will see. Now, just one note about the continuity equation. It is common between SPH practitioners to consider the delta term. So this delta term was introduced first by Antuono in 2011, and it is used to stabilize the pressure field. I mention this because, okay, so it is calculated in general in this way, where this is a special form of the gradient of the pressure field. So I mention this because we will later discuss the use of the delta term when talking about the time integration scheme. Now, let me quickly present the integral versions of the discrete SPH operators. So here is the divergence, the pressure gradient, the Morris Laplacian, and the Monahan Cleary-Gingold Laplacian, which is another version that we will be discussing. Now, here note that whenever the domain of integration coincides with the space, or considering the fact that the kernel is compactly supported when we are far enough from the boundaries, this term, these two terms that we have added in the discrete level, vanish in the integral level. So these are consistent with the convolution definition that we made at the beginning. Now, a few words about the consistency of SPH. So at the integral level, the consistency is of order 2. This is a well-known fact, and you can find many mentions in the literature. At the discrete level, on the other hand, things are a bit more complicated. I would like to highlight the expression obtained by Quinlan and collaborators in 2006, where the consistency error of the SPH approximation of the gradient of a function was given by this expression here. There are several terms involved. I want just to highlight the role played by the eta parameter, which shows to play a role in the consistency as well as in the convergence, as we will see. Very well, so here finishes my introductory part. Now I start with the presentation of the convergence results. Prior to that, I would like to show the mathematical conventions that we have followed. So we define the direct and inverse Fourier transforms in this way, and a consistent definition of the convolution is also used. So when we start to study the convergence of SPH, we decided to pick an easy problem and see how we could apply Fourier transforms to the study of the convergence of this problem. So we choose the one-dimensional hydrostatic problem that is described by this ordinary differential equation here, where we consider an infinite depth and a free surface, so a boundary condition at x equal to 0. An homogeneous Dirichlet boundary condition is used in this problem. The integral SPH version of this problem is given by the integral equation on the left. So regarding this problem, the SPH problem is also relevant because it is linked to the still water tank test that is commonly used in SPH in order to assess the stability. Also regarding the consistency, I'd like to mention the results by Colagrossi and collaborators, who showed that actually using this precise form of the pressure gradient operator is inconsistent. In this work, they proposed several alternatives, but I will focus in any case in this version of the operator, because the other alternatives were present several difficulties when studied using Fourier transforms. So as our goal was to understand the use of these techniques in SPH problems, we decided to focus on this version. Now, regarding consistency, the consistency error of this problem is given by this expression here, where, as you can see, whenever the boundary condition is homogeneous, and this is a relevant fact, because if we have a background pressure different from 0, the problem is not consistent. But whenever this is satisfied, the consistency error is given by this expression, so it's of order h, except at the boundary, where the problem is inconsistent, the operator. Now, concerning convergence, we obtain this bound for the error. Note that here, as the integral of the kernel is considered to be equal to 1, then its Fourier transform evaluated at 0 should be 1. So when h tends to 0, this tends to 1, and this vanishes, therefore establishing a bound for the error. Now, this inequality is obtained when these two terms are closed. If not, we cannot obtain this bound for the error. This states that as you see, that the SPH approximation of the error is close to the error itself. So maybe this assumption presents several inconveniences. I won't discuss these details now. Simply, the details are included in chapter 5 and also were published in this article in Computer Particle Mechanics. But when going to the discrete, what we found is that when we pick constant values of the eta parameter, at first we selected several values, and we observed that the SPH solutions converge towards the hydrostatic field. So here I have depicted in the vertical axis the pressure, and in the horizontal axis the x coordinate, so the depth. These SPH fields converge toward the hydrostatic pressure. But then when we went to study the case with eta tending to 0, we observed that depending on the choice of the kernel, the solution was not convergent. Here I have depicted in the vertical axis the error expressed in terms of a discrete version of the L2 norm. And here we have the smoothing length. So as the smoothing length tends to 0, not all the kernels lead to convergent solution. After that, we decided to extend the study of the case with eta constant to a more general case and do it more systematically. So we selected different ranges of this parameter and found that the condition number of the matrix involved in the problem at the discrete level, here I have depicted the condition number, and here it is the eta parameter. Different colors correspond to different kernels. The 3 well-known kernels are considered. And we found that for certain ranges of eta, the condition number reaches certain peaks that lead to non-convergent solutions. So here, the parameter eta shows its role also in the convergence. Now, all this work is included in chapter 6 of the thesis and was also published in the following article in Journal of Hydrodynamics. So with this, I will start with the main part of the thesis, which concerns the advection-diffusion equation. Okay, sorry, I don't know how to. So, concerning the study of diffusive problems in SPH, I would like to highlight the work by Biolo and collaborators, who in 2018 showed that, studied the spectral properties of the matrix involved in the Laplacian operator at the discrete level. There is also the work by Bassa and collaborators in 2009, where they studied the consistency of SPH Laplacian. Now, in this work, the focus is set on studying the integral SPH approximation to this particular form of the advection-diffusion equation. 2 remarks: we considered the whole space as domain for the problem, and at the first attempt, we consider the advection velocity v to be a constant field both in space and time. Now, the exact solution to this equation is given by this expression here, where we have the Fourier transform of the initial datum, and this symbol here stands for the inverse Fourier transform that affects the whole expression. I would like to remark that we have here the Fourier representation of the exact form of the advection operator, as well as the Fourier representation of the diffusion operator. Now, one of the goals is to obtain a similar expression for the SPH equation. This is the integral SPH version of the advection-diffusion equation. I have done nothing but substituting the exact operators by the SPH version at the integral level. Now, if we take Fourier transforms here, we obtain the following expression, where again we have the term corresponding to the Fourier representation of the advection operator. Here, little w stands for the radial profile of the kernel's Fourier transform. I have used here that as the kernel is a radial function, then its Fourier transform is also a radial function. Therefore, I can define a radial profile for this. And now the same is obtained for the Laplacian operator. Here, the function phi is still a generic function that we don't know, which represents the Fourier representation of the SPH Laplacian. So one of the goals is to obtain an explicit expression for this function. This is the explicit expression of the SPH solution to this problem. So the theorem stating the convergence is the one here. Basically, it says that whenever the kernel satisfies the positivity condition that is written here, and provided that the initial datum satisfies certain regularity, smoothness conditions, then the integral SPH solution to the SPH equation converges towards the exact solution. I will now sketch the proof of this theorem. This proof is divided into 2 parts. First, I show how we can obtain the Fourier representation of the SPH Laplacian. And second, I will finish the proof by showing how we can establish a bound for the error using both the consistency and the stability properties of the SPH problem. So we consider here only the case of the Morris Laplacian. The Monahan Laplacian is also treated in the thesis, but I will just do in full detail the obtention of the function phi for the Morris Laplacian. This is an alternative definition of the Morris Laplacian, where I used the function gh, defined in the same way as the kernel, by scaling a function g defined in terms of the derivative of the kernel's radial profile. So now I rearrange terms in the integral above, and I can rewrite this expression in this way. Taking Fourier transforms, I obtain this expression where I have used that the Fourier transform of a convolution is the product of the Fourier transforms, and the integral on the left is simply the Fourier transform of GH evaluated at 0. So now it only remains to compute the Fourier transform of G. I have here rewritten the expression of G. Now, passing the x squared to the other side, I gave this expression, and considering that the Fourier transform translates derivatives into products and products into derivatives, I obtain the following expression for this equation in the Fourier space. This equation can be simplified, taking into account that the Laplacian is the divergence of the gradient. And now, similarly to what we done for the kernel, and considering that the g function is also a radial function, we can define the radial profile of the function g and rewrite this expression, also considering that the gradient of a radial function can be expressed using the derivative with respect to the radial variable. We obtain the following expression, which is a simple ordinary differential equation for f that we can integrate, leading to the following expression. And this can be also rewritten to obtain the function phi that appears in the positivity condition. This function phi defines the Fourier transform of the Morris Laplacian. I will later discuss about the nature of this function. Now, coming back to the expression of the Morris Laplacian, I have the functions g here, it's the Fourier transform, and taking into account that f is the radial profile and the equations above, I obtain finally the expression for the Morris Laplacian. Very well. So the proof continues by establishing a bound for the error expressed as the difference of the SPH solution and the exact solution in the Fourier space. This error satisfies a non-homogeneous version of the advection-diffusion equation presented above. So using Duhamel's theorem, we can obtain the following representation for this error, where the function f is given by this expression. Now, as we already know, the Fourier transform of the kernel, and also the function phi, we have already obtained it, we can use the properties to establish a bound for the error. Now, 2 remarks here. We have already an h squared that it is interesting because it shows already that we may have a 2 order of convergence. But the proof is not finished yet because we have this term here that still depends on the time. Now I am going to use the stability. Here I have used the consistency properties, and now I will use the stability properties of the problem to finish the proof. So the SPH solution is given by this expression that I have already shown. We can express the module of this function in this way, and note that the exponential term is smaller than 0 whenever the phi function is positive. So this is precisely the positivity condition, which actually is an stability condition, and that allows us to establish a bound for the module of UH, and therefore, introducing this here, establish a bound for the error. So 2 remarks about the positivity condition. First, note that this condition is weaker than asking the kernel to have a positive Fourier transform. Note in particular the cases with positive Fourier transform, like for instance the well-known kernels, provided that this integral is computed from 0 to 1, so everything is positive here, so the condition is automatically satisfied. However, these do not imply that there are some kernels with not positive Fourier transform that also fulfill the condition. Actually, we have numerically shown that the cubic and the linear spline, and I will now show you the results, also satisfy the positivity condition while they do not have positive Fourier transform. Second remark, the positivity condition is used in the proof of the theorem as not as a necessary condition, but rather as a sufficient one. However, we have picked two examples of kernels like this one here, not satisfying the positivity condition, and none of them leads to convergent results. So, well, this result suggests or may suggest that actually the positivity condition could be a necessary condition for the convergence. Now, in the case of the Monahan Laplacian, we obtain this expression for the Fourier representation of its Fourier of the Monahan Laplacian. Here, the function phi is a different one, but there is also our already known phi involved there, as well as this other function that appears in the function phi of the monocle Laplacian. Now, for the Hessian matrix, in the version presented by Español and Revenga in 2003, the Fourier representation has also been obtained. I won't be discussing this obtention, the obtention of these terms here. The details are on chapter 7 of the thesis, and also they were published in the following article in the journal Computer Methods in Applied Mechanics and Engineering the last year. Now, after that, we decided to go for a more complicated problem, and we decided to study analytically the case with a constant rotation velocity field. Now, in this case, the theorem can be written in this way. The proof is quite similar to the other one. There are some differences, but the idea is mostly the same. Now, these results are included in chapter 7 and were also published in this article in Acta Mechanica Civica. Here, I show you the results, the numerical results, referred to the case of the rigid rotation. So for this problem, we decided to pick a Gaussian function as initial condition that rotates around the origin. This is a typical benchmark case in the context of studying the advection-diffusion equation. In particular, it was used in the work by Pedro Galán and collaborators in 2011. Now, in the left, you have the initial datum as well as the particle setup. And on the right, you can see the curves of convergence. So here in the vertical axis, I have depicted the error in terms of the discrete version of the L2 norm. And here we have an adimensional form of H, so the smoothing length. You can see that all the kernels considering, which include the linear and cubic spline, as well as the one-line kernels, converge, and the order of convergence is H squared. So we believe that this is an interesting result because we show that kernels not having positive Fourier transform also lead to convergence, at least in the integral level, because here the interparticle distance is always chosen smaller with respect to the smoothing. Small with respect to the smoothing, sorry. Okay, now let's discuss a different problem. Here you see a simulation that has been generated using a quantity SPH. So this is a frontal jet impact generating a shock wave. It has been generated using a discrete version of the Euler equation. So there is no diffusion in this problem. I have already mentioned that the delta term is used in order to render the pressure field stable. Here you can see the pressure field that mostly remains stable. We can see actually the shock wave traveling from one extreme to the other of the domain. And no delta term has been used to generate this simulation. So the stability is attained by integrating in time using an implicit integrator scheme. Now, this result was first presented by José Luis Cercospita in the SPHERIC workshop in the year 2020, and also published in the following article in the European Journal of Mechanics. So we believe that this is an interesting result, as to the best of our knowledge, is the first stable simulation presented of a non-diffusive case without using delta SPH. Now, regarding the time integration, the role of the time integration in the energy conservation, the power balance of the SPH scheme that I presented before can be expressed in the following way. Here we have the kinetic power, the power due to the gravity, the potential forces, the power due to compressibility, the power dissipated due to the diffusive terms, and here an extra term that is added to take into account, depending on the value of A, the different possible choices for the pressure gradient over heat. This term is linked to the level of particle disorder. I won't discuss about this now, so let us focus on the role of the time. So you may note that I have made explicit the dependence on the time of all these terms. Now, actually, these quantities have been considered here as continuous functions on the time, because we have talked about the spatial discretization, but we have said nothing about the discretization in time. And obviously, the discretization in time should also play a role. So what we see is that actually, when going to the discrete scheme, some of these quantities cannot be computed in the same way. So we have to define discrete versions of these powers, and this introduces an error term here, which takes into account the error due to the time discretization. This time discretization obviously should depend on the scheme that is used to integrate in time. Here I show you the results for the Hoyne scheme, which is an explicit predictor corrector method, and an implicit midpoint method. So different colors stand for different current numbers. The dashed line corresponds to the error due to the particle disorder, so the second term that I have added in the equation before. I won't discuss that now, but the solid line corresponds to the error due to the time discretization. You can see that for much smaller current numbers, smaller errors are obtained with the implicit midpoint scheme. So the conclusion here is that the use of an implicit integrator not only allows for reducing the error in time, but also leads to stable simulations, in principle, not needing to, without the need of use the delta term. Here finishes my presentation about the mathematical aspects that have been treated in this thesis. Now I will present an application case. So this is a video of the dam break experiment that has been carried out at this faculty. The setup of the experiment, and actually the same facility that was used in Lebowski and collaborators 2015, is used here, with the difference that an obstacle is introduced in the setup and placed in different configurations in order to induce three-dimensional effects in the flow. So here you can see one of the configurations with the obstacle placed at one side. So here is a non-symmetric flow which is generated. In the second configuration, the obstacle is placed in the middle, generating therefore a symmetric flow. Now the pressure has been measured, you can see the cables here, using 3 sensors. These sensors are placed at the same height, so that the hydrostatic component of the pressure is the same for all of them, but at different transversal positions. This allows us to capture the effects on the pressure field of the three-dimensional nature of the flow. Later, we will see if the SPH solver is capable of reproducing these effects or not. Now, the dam break case has been widely used in the SPH literature in order to validate SPH. However, the experiments that are used are not always properly statistically characterized. So here, following the perspective used in Lebowski and collaborators, we have performed up to 25 repetitions of each one of the cases considered until the main statistical indicators, here the mean and the standard deviation, converge toward constant values. Here on the left, you have the mean, and on the right, the standard deviation, depending on the number of repetitions. So these are actually running mean and running standard deviation. Different colors stand for the different pressure records obtained with the different sensors and for the 2 cases that are considered. In this case, this case here of a higher pressure is the pressure, actually this one here, corresponding to the sensor which is most exposed to the flow in the non-symmetric configuration. So the confidence intervals of the 95% have been obtained for all the pressure records. Here you can see the pressure records of the 3 sensors in the non-symmetric configuration of the obstacle. The different colors stand for the records obtained with different experiments. And the dashed black lines are the percentiles that have been obtained, which are interesting to us because we will use them in order to see if the result obtained with SPH lays within the experimental confidence intervals. Now, these results have been collected in an article that is actually finishing to be sent for submission at the Journal of Fluids and Structure. Now here we can see a video of a numerical simulation of this same 3-dimensional dam break test. We have considered different kernels, including the 3 well-known kernels and also the cubic spline. And the boundary integral is used, the boundary integral technique is used to deal with boundary conditions. In particular, the formulation presented by Calderon and collaborators in 2009 is used. In that formulation, a kind of potential of the kernel is defined in order to be able to compute the Shepard factor close to the boundaries. So in this research, we have computed the value of this potential for all the well-known kernels and also the cubic spline as well as the Gaussian kernel. Delta SPH scheme is used in this case, as well as a Hoyne predictor corrector method. Now you will see in the next experiment, these cases, by the way, these videos correspond to the Wendland kernel C4. You can see that the pressure field, now in the next video, presents certain stabilities that I believe that are certainly related to what we have seen this morning in the presentation of Professor Mateo. But the hydrostatic structure is, in any case, well conserved. Now, regarding the results of the pressure, here I have shown you the results for in the non-symmetric case. This is the first pressure record, which is the one which is most exposed to the flow impact, and this is the one which is placed behind the obstacle. You can see that there is a lot of noise in the SPH solution corresponding to the roughest in particle distance. Actually, different colors stands for different interparticle distance, and the eta parameter has been kept constant. However, the SPH solver properly captures the pressure peak, so we actually are able to compute the impulsive load properly using the SPH scheme. This is not the case in the sensor, which actually does not correspond to an impulsive loads according to the standard of impulsive loads defined in the work by Loisel. And here we believe that this happens because these simulations are monophasic, so only the fluid is, only the liquid is taken into account. And in the experiments, we see that the presence of air bubbles are important in the region where this sensor is placed. So we believe that the air phase plays a role in diminishing the value of the pressure, and this is the reason why this pressure is not well captured. In any case, I would like to highlight the fact that the industrial concern is mostly about the impulsive loads, which are the maximum loads. So I would say in that way that this scheme using a monophase approach is sufficient in order to match the impulsive load. Very well, so here finishes the presentation about the content of my presentation. Now I will talk about some conclusions and also discuss ideas for future work. So the first conclusion is that the convergence of the hydrostatic, the SPH integral hydrostatic problem has been established, and it has been studied numerically and analytically in both cases when eta is kept constant as well as when eta tends to zero. The convergence of the integral SPH advection-diffusion equation has been established at the integral level. It has been shown that in order the solution to be convergent, we need the kernel to satisfy the positivity condition. This is, we believe, an interesting fact, because this condition is weaker than the positivity of the Fourier transform. So we think that it is an interesting result regarding convergence. Now, the error in the energy balance due to time integration has been investigated, and the use of an implicit time integrator scheme allows for avoiding the use of the delta term, as well as leads to reducing the error due to the time integration. The experimental data of the dam break case has been, experimental data has been generated, and it has been statistically characterized. I'd like to mention the fact that this data will be publicly available once the mentioned paper is published. And also, the experimental case has been studied using aqua GPU SPH, show good agreement with experimental results in the case of the impulsive load, while other pressure records that are linked to other more complex phenomena are not well captured by the algorithm. Now, as ideas for future work, first, extend the analytical study of the advection-diffusion equation to the discrete SPH scheme is considered in the case of periodic problems. So the idea is to use the Poisson summation formula in order to assess, using the Fourier transform tool, in order to assess the discrete problem. Also, and as a more future goal, the study of the convergence of the Barger's equation is considered as a desirable goal in order to approach the study of the convergence when concerning the Navier-Stokes Equations. So another interesting research could be the study of the Poisson equation using the same methodology that was followed to study the hydrostatic problem at the discrete level. So I'm thinking about the study of the influence of the eta parameter in the condition number of the matrix. Why this may be interesting? Well, the hydrostatic problem is never solved as by inverting the matrix of the discrete problem. However, the matrix corresponding to the Laplacian is inverted to solve the Poisson equation in the context of ISPH, so incompressible SPH, which is another version of the method that I have not discussed. But in that context, the study of this equation using this methodology would be interesting. Furthermore, this way of solving the Navier-Stokes equation by a projection method, and using the Poisson equation is also used in the context of other CFD, like for instance, finite volume method. So this may also give some insight for other computational methods. Also, test the downbreak case in the computational level. Using the time integration scheme is obviously considered as a required future work for this in order to see if the results obtained for simple problems also translate into more complex geometry. Also applying multi-phase simulations in order to study if this has an effect in the obtention of other pressures involved in the aforementioned experiment is considered. And finally, the use of aqua in order to simulate real life or more real application cases involving already waves with breaking events and also floating objects is considered. I have to say that this is actually work in progress. So prior to finish, I would like to have a word to say thanks to both Fabricio Maciá and Antonio Soto, who has been my supervisors, as well as to Professor Ricardo Zamora and Professor Juan Miguel Sánchez. All of them were an inspiration for me at the time when I was a student at this house. Thank you very much.